Okay, so last day. So folks, a historic day in my life. After 39 years of teaching, this is my final class. And I must say, it's somewhat poetic. There's nobody in the classroom but me. And I'm talking to a computer screen. So I think it's time for me to hang it up. But anyway, okay, so as far as primary, secondary here, I'm going to drone on for a while today. I looked through to the end of the document, and I finally have to admit that I don't have enough time to do everything in this that I would like to do. And so I'm going to get us through what I consider the essential information today. I'm not sure how long that'll take, probably 45 minutes to an hour, and then I'll show you some stuff at the end that gets pretty detailed. I mean, it's pretty good, but nonetheless, we just don't have time. It would probably take at least one, if not two more classes to do this the way I would like to do it. So as far as testing, exam, you'll just be tested over the stuff that I talk about. You know, I'll make sure that I pull any questions that I might have that refer to the other stuff. So at any rate, let's go ahead and get going. This is where we wound up last time. And, you know, this is just looking at different applications. This is a boiler chiller changeover. And this is about as simple as you can make it. Most of them are more sophisticated. We've got two or three more on down in the slides that get extremely complicated. And, you know, we're probably going to just brush over that. But, you know, the interesting concept here you have to realize is that this would be for a two-pipe system. So a two-pipe system means I've got one coil in my space. I can put hot water through it and get heat, or I can put chill water through it and get, you know, air conditioning, but I can't do them both at the same time. And so this shows, you know, a central piping system that has a boiler and a chiller connected to it. And of course, you know, to save money, there are systems, schools, for example, that, you know, it can be chilly in the morning and they need to provide heat to the campus. But then later on, past 10, 11 o'clock, it starts heating up. And then with all of the people in the rooms, the loads, the cooling load becomes significant. And then they have to provide cooling. And, you know, they were too cheap to buy a four-pipe system. And they didn't want to buy the, you know, and put two coils in every space so you could circulate them both and then let the controls pick. So you actually do a changeover during the day, and then, you know, from heating to cooling. And then once the sun goes down, it gets cold outside, you go back to heating, and you do that, you know, a lot of different days. Excuse me. So you have to be a little careful, you know, because that chiller, it really doesn't want to see 140-degree boiler water. That's a good way to wreck a chiller. And that boiler doesn't want to see 42-degree chill water. It's going to be a bad day in the plant if you do that. So you've got to have some sort of controls on this thing that will, let's say you've been on heating, you turn the boiler off or you stop that circulating pump, but you have to continue to circulate that water through the loop, because the only way you really have to cool it down is to put it through the coils in the space and put that heat into the building. Now, you would hope that you time this appropriately so that those people want that heat and that you don't, you know, warm them up and make them comfy, and then you overheat them to cool the loop down. And then you get the water cool enough, say 80 or something, 75, 80, that you could start bleeding it through the chiller. And then the chiller has to cool the loop down before you can start doing air conditioning. And you just have a big control mess. And so that's kind of what these systems have to accomplish if you have a two-pipe system. And there are buildings at Tech that have a two-pipe system. So I'm going to move on from this. I'm not going to read all that to you. I want to get on here. Okay, this is looking at modulating three-way valve control applications to primary, secondary. This is what he calls his preliminary discussion. And so he's got three different layouts here. This would be for a mixing valve. And of course, remember, there's a diverting valve and a mixing valve. And I guess the mixing valve has got two innies and one outie. And the diverting valve has what, one innie and two outies or something, you know, it's just kind of they're the opposite of each other. But anyway, so he says this is one way this stuff's been done in the past. And he's going to have some comments on the good, the bad, the ugly here. But you see, we've got our pump. We're continuously pumping the secondary. We've got a crossover bridge. We put our three-way valve here to control how much water comes up into the secondary. And we've got our bleed return riser. When we're taking water from the primary into the secondary, we got to bleed some water back out to the crossover bridge that goes back to the return. So then you probably figure out kind of how that operates. Well, here's another. This is bypass or diverting valve in the secondary. And so you see this one has one in and two outs. And so you just slightly different valve, and you put it in a different location in the circuit, basically doing kind of the same job. Okay. And then this is what he recommends. And now we'll go back and read the comments. So it's kind of like the good, the ugly and the bad, and this is the good. It's in reverse order. So this is their recommended arrangement if you're going to use a three-way valve. And notice that we're showing the three-way valve down here in the crossover, and that makes the common pipe move up here as part of the secondary. Kind of interesting. And we'll see his comments in a second. If you look on these, then our common pipe is in the crossover bridge where we're kind of used to seeing it. Okay, let's look at the comments. The arrangement shown in figure 60 overcomes problems and is highly recommended. Arrangement has these advantages. Okay, control valve is sized to the crossover bridge flow rate, which is always the controlling flow rate. So say this is the flow rate that you have to control, is the primary water that's going through the crossover bridge. Well, so if your flow is the same, if it's a cooling application, then this flow rate and what you're circulating up here is probably going to be the same, and this is not so critical. But if you're in a heating application, you may have, our old example is we have 10 GPM up here and 40 GPM up here. So if I put that control valve in the secondary, like we show up here, then I'm trying to control 10 GPM with a control valve that's sized to handle 40 GPM, and my controllability sucks, you know? So let's get smart and realize that in a heating situation, this is the control, this is the flow I have to control. So let's put the valve down here where it can be sized, what, in there, he's sizing that 1 1/4 in the pipe sizing example. And so we get a 1 1/4 inch valve, which is cheaper, and will control this flow much better than a 2-inch valve sitting up here that's sized for 40 GPM. So that's the first advantage of this arrangement, whoops, over those previous ones. Okay, so that makes sense. The particular location of the three-way valves requires an underslung bleed riser if the operator, and this is like on the control valve, is to be placed at the top of the control valve. Okay, that's really getting down into the details of it. But the underslung bleed riser provides the thermal anti-gravity flow leg and eliminates the need for flow control valve. So we remember that from the underslung bleed riser discussion, hopefully. Pressure 3, pressure at the secondary pump can never be less than primary circuit pressure as developed in the crossover bridge. And so remember, let's see, go the right direction here, that this is the point of no pressure change. And so, the connection at the common pipes, I guess it's up here, as And so when this pump operates, it's going to then, there'll be a slight pressure drop here, but then we get the increase in pressure all the way around here. So now that comment is not really true from this point to the pump, but you make that as small as possible. So in general, it is true. And the crossover bridge can be balanced by proper selection CV of the three-way valve. So, you know, if we select our CV appropriately on the valve, then that's part of the balancing, even though we're showing balancing valve in the crossover anyway. Okay, so with a three-way valve, that's the recommended procedure. Okay, what do we got here? Let's see. Oh, okay, this just shows it with overhead piping. If you have the overhead piping in this leg, you got to put that check valve, that flow control valve, to prevent any gravity circulation up into that secondary. So that's not much. Well, let's see, what do we got here for the applications? Secondary zone pump is in continuous operation. Secondary zone water temperature is modulated up or down depending on the amount of primary water that gets admitted to the secondary. Control of secondary circuit is just vested in water temperature change. Now remember from our control valve sizing presentations, we could control with flow or we control with temperature. And that temperature control curve was that nice 45-degree line, which was ideal. And so temperature control at constant flow gives you better control than that flow control, because remember, especially on a 20 delta T coil, you had that kind of banana looking curve up at the top where you had to reduce flow to, like, I don't know, 10% to get a 50% reduction in heat transfer. And so that would be that would be an advantage of this type of arrangement, that you get temperature control instead of flow control. And so your control system would probably be better and occupants would probably like it more. But you got to buy these three-way valves and this, that, and the other. And, you know, it's cheaper to turn a pump on and off, you know, because you got to have that little pump anyway. So you just turn it on and off under the action of the thermostat. You don't get as good control, but the guy paying for all the equipment doesn't have to spend as much money. So there you go. It's a trade-off. The continuous flow established by primary secondary arrangements has important advantages where secondary zones are to be separately reset. And so, you know, with those three-way valves, you can reset that water temperature with outside air or with anything you want to. And of course, it also provides freeze protection because we're pumping the coils continuously. I think we've done enough of that. That was fine. So yeah, you can read through those, but I think I pretty well talked through that. Okay, so here's an example of just actually doing the CV sizing. And of course, you know what I did. I left my calculator in the classroom, but we know this equation. So you see here, this is the chill water application where I got 40 GPM everywhere. And so to size that CV, and again, our sizing criteria here, they're showing as a minimum of 10 feet across that valve. Okay, so to calculate that 19, what do? You take 10 feet and divide by 2.3 to get it in PSI. You take the square root of it. We're taking specific gravity to be 1 here. So you just take the square root of that and you get 2.08. I've got that number memorized. And then you divide that into 40 because the valve equation is what? GPM Q is equal to CV times the square root of delta P over specific gravity. And it comes out 19. I checked it this morning. So, you know, you guys are more than able to size the CV for that. If you come down here. And of course, we see the pipe size here. We got 2-inch pipe every place. So that would most likely be a 2-inch valve, maybe a 1.5, depending on what you had to do to get a CV of 19 from your valve supplier. And then this is the heating situation where we got 10 GPM in the crossover and 40 in the secondary. And so the CV now drops to 4.8. Again, you take 10 divided by 2.3, take the square root of it, and take that result and divide it into 10. Your flow rate. CV comes out 4.8. So that's what you should size that valve for. Pretty good, pretty good. Let's see, modulating three-way control application to primary, secondary. So we just have some applications here. Really good for temperature reset. So, usually we show these two bulbs. When you see the double bulb, this is in the outside air. This is, I guess, on the water that we're circulating. You got some sort of a schedule programmed in this thing. This valve modulates to give you the proper water temperature based on outside air. We could also do that same thing. Well, we could do reset, or this could be just a simple thermostat setting, and we're going to bleed primary water into the secondary in order to keep the thermostat in the space, within its control range, probably plus or minus a degree or a degree and a half, something like that. Keep everybody comfy. So we could do that. Let's see. Space temperature control. What are we doing here? Oh, freeze protection. So, I mean, it's the same picture. Just the idea is that this is controlling discharge temperature from an air handling unit, and we get freeze protection because we're pumping the coil all the time. So this thing it's kind of redundant in places. We can do the three-way valve on a circulated domestic water storage tank. So you see, as we go through this, we've got different ways to do all of these things. And some are going to give you better control, but they're going to cost a little more. And so the designer has to pick, could talk about it with the owner, whatever. But so here's our domestic water tank. It's not labeled, but so this is our circulating pump that circulates out through the building to make sure that everybody has hot water close to them. So when you open a faucet, you don't have to wait for, 10 minutes for the hot water to get to you. So this is going to be whatever this tank, maybe it's 180. You're going to be circulating 180-degree water around in a circle, and then everybody pulls off, and they got 3 or 4 feet of pipe, which takes about 10 seconds, and all of a sudden you got hot water. Voila. This is our makeup line coming in. As we bleed water out of the system, the pressure would fall, and this would be our fill point. So then we're putting cold water into the tank, and then we're circulating on this side. We're continuously circulating on this side of the loop. I got my heat exchanger over here. This could be steam or hot water. Wild indicates I have no control. It has plenty of capacity. And then this valve is simply modulating to heat this water up to say 180. If that's my set point, 180, something like that. You might set this 182 or something just to make sure that you keep up a little bit. But probably if this is a 180 tank, you set this on 180. This circulates all the time. The cold water comes in here, mixes immediately in the tank, and this circulates continuously, and we bleed in heat as we need it here. When this valve lets some of this hot water into here, then some of this return flows through the heat exchanger. So, bingo. Let's see, industrial fluid temperature, similar sort of thing, just a different application. I think I'll just pass over that. If you understand figure 67, you'll understand figure 68. And here's more changeover stuff. Oh my goodness, this stuff starts, this starts to become more realistic here. And I guess we've got time to read a little bit of this. He's got great notes in here talking about this. And later on, he's got a system that's so darn complicated that you can't hardly understand it. And he doesn't really explain that one. I think this one gets explained pretty well. But here's your system pump that's circulating. And then I've got a separate little circulating pump on my chiller to pull cold water out of the chiller, which then can go up here to the system. And then I can get some warm water from the system and put it back through my chiller, and a similar kind of arrangement over here on the boiler where it's got its own. And, you know, I can do reset. I've got outside air sensor over here. I'm doing reset, and I've got protection, you know, set to 80-degree bypass, 70-degree closed. So what they're saying, if that water is 80 degrees or above, I'm not going to put it into my chiller. It's going to have to circulate until it cools down because I don't want to wreck my chiller. Let's see, I guess we'll go through a little bit of this notes. For heating, the boiler pump flows the boiler continuously at an established flow rate. So I'm gonna run this boiler pump all the time, but it may be going around in a circle. It depends on the action of this control valve, whether I'm letting any of my system water back through to actually get heated up, to put some cold water back in here so the boiler will fire. You know, I can, if I just circulate that loop and it's hot, then the boiler controls will just shut down the flame and it'll just sit there until it senses, you know, a water temperature drop. So let's see, the three-way valve, let's see if I can get all this up here. Okay, the three-way valve reset system water as required with outside air temperature, except when overridden by a high temperature different signal between the boiler supply and return, which might be after we've been on the chiller and we got cold water and we don't want to shock that boiler. So we're going to protect it. So you've got some protection, and the same sort of thing is going on with the chiller. You can read that, but and then three-way pipe. I'm not going to talk through this. I'm not aware of anybody that really does three-way pipe stuff anymore. The idea is I've got hot water coils and chill water coils, and I've got two different distribution lines, but I've got one return line. So I'm going to dump the return out of the hot water coil and the return out of the chill water coil together and mix them. And then I'm going to take that and split it and put it back in the boiler and chiller. Well, that's an awful idea. The energy guy just, hey, buy an extra pipe and you can have a 4-pipe system, and then you don't have to do that. But you can read through here. And then I'm going to skip some of these. Okay, this is what I want to get down to. So this is the main topic for the day, this 21 here. Modulating two-way valve control application to primary, secondary. So and this is interesting the way this works out. So the crux of the matter here, if you do this right, it's really, really good. And if you do this bad, it's a disaster. So this is danger, danger, danger zone for the mechanical engineer if he doesn't know what he's doing. And they do a pretty good job of pointing that up here. So modulating two-way valves are applied to primary, secondary control. Their proper application leads to superior performance, not just good performance, but superior performance. Improper application, however, will land you in court in a lawsuit, which you don't want to be there. I've been there. It's not fun. You don't want to go. However, it can lead to serious operating problems. The typical application is shown below. Okay, so the way we make this work is, you know, we've got our secondary, we're going to circulate it. We got our primary or crossover, we got our bleed riser and bleed return, and we're going to put a two-way valve here, and we're going to put a balancing valve up here, because when this valve opens, we have to have a pressure drop across the primary to force flow up into the secondary. If you don't, you won't get anywhere close to the proper amount of flow. So this thing gets balanced with this open so that we get the desired flow from the crossover into the secondary. So that's what is supposed to happen. Let's see. Typical application, two-way. In the two-way valve application, the controlling input flow from the primary crossover bridge to the secondary circuit is caused by the restrictive pressure drop in the secondary circuit between the bleed risers, and that's caused by that balancing valve right there. But of course, now Bell and Gossett, they have their special monoflow fittings that accomplish that for you. And they're more than happy to sell them to you because that's why they put all this stuff up there to help sell product. Okay, and so when they show these little diagrams like this with these monoflow fittings, what you should think about is this situation here, because those fittings are establishing the pressure drop across that pipe. Okay, so think this when you see this, and you'll be right. Okay, let's see, bleed flow rate, that's up from the crossover into the secondary, is under control of the two-way modulating valve. Two-way valve control should not be applied to primary secondary arrangements unless there is a complete understanding on the part of the engineer of the fact that a flow variation in the secondary circuit of substantial proportion can occur because of the operation of the valve due to improper flow and pressure ratios. Okay, that's a mouthful. So, but what that's saying is if you don't get the flow ratios and the pressure ratios that we're going to define in a minute right, when this valve goes from open to shut, you will drastically affect the flow rate in the secondary. And that is not your intent. Our intent is to have a constant flow rate in that secondary. But if you screw this up, when this thing goes to open to shut, you may change the flow rate up here by 75 or 80%, which is going to make it darn difficult to keep those people comfortable in that secondary. So again, danger, danger, danger if you don't read this and understand it. And so that's what we're going to do. Reductions in secondary flow rate from the control valve wide open position to the control valve closed will depend on these two factors, these two ratios. The full load or design ratio of secondary flow rate to primary input flow rate. Okay, so, you know, you take your secondary flow rate and you take your primary flow rate and you calculate the percent, as we'll see here in a second. And then the second thing is the ratio or the percent of the restrictive flow causing pressure drop in the secondary circuit to the total secondary circuit pump head. In other words, that's awkward. Whatever this pressure drop is across here divided by the total drop for the entire secondary. And then the first one is the flow up through the bleed riser divided by the secondary flow rate. So that, so to get this right, you have to calculate those, and they have to be within a certain ranges. Okay, and so this is, he's just showing the diagram. So here's the restrictive drop, Y, he's calling Y. So that's the PSI, I guess at 1 minus the PSI at 2, divided by the total pump head in the same units, either feet a head or PSI. And then here's the input flow from the crossover bridge to the total secondary flow. Okay, well, let's look at what happens. So, and it takes a minute to let all this sink in. So up at the top, across the top, I've got the percent riser input flow to secondary. So that's A over B. And so A is what's coming up from the crossover, and B is what's being circulated up here. So we just take that, and he's done it in a percent, okay? So, you know, if we've got really hot water, then that crossover flow is small. And then we, you know, we do that mixing thing, right? Here, let's put it up here. Yeah. So if this is really, really hot water, this 250-degree water, then I bring it up here. And so this might be, you know, 5 GPM, and this might be 20 GPM that I'm circulating. So then 5 divided by 20 would be 25%. Okay. And so then you would look in that table at the 25%. Then, of course, the other thing is you have to look at what your delta P is across here divided by this total pump head. That's the other one. Okay. So that's the riser input flow to secondary flow in percent. And then on this y-axis over here, this table of the coming up and down on the table, we've got the percent restrictive pressure drop to total pump head, and that's the secondary pump. Okay. Well, so what you want, and this is the change in flow as you go from full open to full close. So you want this to be 0. Okay. Well, and so you can see if I'm up here in this region, well, I'm probably pretty good. If I'm down here in this region, this dog, as we say in Tennessee, this dog won't hunt. You know, it's not going to work. You in lawyer territory down here. You in getting paid and getting the Christmas bonus territory up here. Okay, so this is the good side and this is the bad side, and then it just kind of depends where you are on these ratios. Probably any place up 10% or less you probably can live with, and it'd probably be okay. So just to pound home again, Table 2 illustrates that two-way modulating valves have limited but valuable application to primary-secondary control arrangements. Two-way valves should only be applied when the input or controlling flow is a small portion, less than, say, a third, so that would be 33% of the secondary flow rate, and preferably when the restrictive pressure drop is less than 25% of the total secondary pump head, circuit pump head. Okay, so just want to let that sink in for a minute. Make sure that you're good on those, because you could actually wind up. Some of you could wind up in a position of doing some of this, and you sure want to understand what you're doing. The rule stated above still leaves considerable application room, especially for deep temperature drop hot water design, as shown in the two-way valve application examples on 49. So you go back and look at those, but this is one of them. And so you see here, this is where this is probably going to work. I got 240-degree water, and I'm going to mix it to the point that I have 150 over here, and I've got a 20-degree drop in my secondary, and I've got, what is that, 110-degree drop for my primary water, because I'm 240 here, and I'm going to return at 130, and so, that's pretty good. Let's see. This is low temperature water. He makes a note that 300-degree water temperature supply systems would be medium temperature water, and that, of course, would probably even work better. Okay, let's modulating two-way valve. Okay, let's look at sizing procedures for the two-way valve. Let's see. So let's just take a look at what we've got here. Okay, so let's see. So we've got 10 GPM through the crossover, kind of our typical heating example. So we got 1 1/4 inch pipe, 1 1/4 inch bleed riser and bleed return. We got 40 GPM, so that's our 2-inch pipe in the secondary. And notice he's specing a valve size for 10 GPM at 3 PSI drop, okay? And so 10 GPM, 3 PSI, so you can calculate your CV from that, right? 3 PSI, take the square root of that and divide it into 10, and I suspect you're going to get 5.7, Okay. And notice that this restrictive loss by this balance valve is set for the same 3 psi. So say, think about it, when the valve goes wide open, then, you know, I've got the same pressure drop here as I do here. So there's 3 psi with valve wide open. So I'm splitting that drop. And then of course I got other pressure drop in this system. And I'm not sure, I don't think that they have to be the same. I don't think they're saying that. It just in this example, it turned out to be. But you know, this has to be set so that when this valve is open, we get the appropriate flow up through here. Okay. But there's just an example of doing that. Okay, two-way valve, primary, secondary applications. Oh, the other thing, let's see, did we have, yeah, okay, we can check our ratios here. We should do that, right? Let's see, so that restrictive, all right, I have to get out my phone calculator here. I just don't like my phone calculator, but. And it's because, I gum this thing. Well, come on, phone. All right. I got one that's so complicated here, I probably can't use it. Okay, so, let me have the simple one. Yeah, oh, that's my calculator there. That's the one I carry. Oh, perfect. Okay, so let's see here. We either have to turn the 3 psi into feet of head, or we got to turn the 30 feet of head on the pump into psi. So let's take the 30 on the pump and turn it into psi. So 30 divided by 2.3 is 13. And then I want to take 3 and divide by 13. So I'll divide by 3 equals, and then I'll invert it. So that's 23%. So on the pressure drop, I'm 23%. So I can go up to, let's see, the table here. And so in this application, this is the flow, this is the restrictive drop. So I'm 23%. So I'm someplace, you know, pretty close to 1.5, or well, it depends on which column I go in. And let's see, it's, oh, I'm 25, I think I'm 25%, aren't I? Yeah, I'm 25% on flow because I'm 10 GPM through the crossover, and I'm 30, so I'm 25. I'm 25 and 23. Okay, so you know, unfortunately, if you really want the number, you're going to have to interpolate. But at 25, I'm halfway. 25%, I'm halfway in between these. So what is that? 11.7. So a little less than 6. And then it's going to go up a little bit. So I'm probably 7%. You could do the interpolation. And so that's considered fine for this sort of a deal. Okay. So, you know, all of these are going to be shown for situations where we can put really hot water into it, you know. So he's saying here that my primary drop, say I'm coming up at 240, I'm going back at 140. So I've got a 100-degree drop in the primary, and I got a 20-degree drop up here. So you can just, for your flow ratio, you can just take that. So that says that's 20%. So my flow ratio is going to be 20%. So that's going to lend itself to it. You know, you got to make sure your restrictive pressure drop is correct as well. And I guess we didn't really look at what's going on. But so, you know, this could be multi-story, or this could be all on the same floor and we're just showing it vertical, but we've got 1, 2, 3, 4 air handlers and we're supplying this heating water, 160-degree water to the air handlers for space heating. And they've got what, what's that? That's 2 innies and 1 outie. Is that a mixing valve or a diverting valve? I think that's a mixing valve, isn't it? On the downstream side, I don't know, I forget. Anyway, it's 2 innies and 1 outies, whatever kind of valve that is, because we can come in on this side, we come in on this side, and come out on this side. So anyway, panel heating, that could be buried in the slab. You know, some houses heat that way. It's really quite nice. You know, if you got a bathroom that's got the the heating down elements buried in the floor, you walk in there with your bare feet and it's so nice. You know, and then the floor gets warm and it warms the rest of the room. So you can do that as well. Two-way modulating reset control applied to heating side of heat cool system with wild steam to water heat exchanger. So I don't think I really need to talk through there. I think you're probably getting this. There's some notes. What's going on? Okay. Primary circuit design basics. I think we have an example here. He tells you how to do this, but I think we can probably figure it out. So we're going to have a little primary secondary that we'll see, like here, and he's given us the numbers for it right here. So circuit 1, we've run our carrier program, and it tells I need for my design heating, I need 200,000 BTUs an hour. And I, the engineer, have selected baseboard heating coils, hot water coils. And I have decided to have a 20-degree delta T on all of my heating coils. And so then I calculate the flow rate at that 20-degree delta T. Well, 200,000 is equal to 500 GPM delta T. This is not hard math. You don't have to go to Bruner to get help to do this, I promise. So you take 200,000, divide it by 500 for the constants, and divide it by 20 degree for your delta T, and you get 20 GPM. Okay, so that first circuit needs 20 GPM. And then we're speccing a 200-degree mean temperature, which means that my supply temperature has got to be 110 and my return has got to be 190. Right? Pretty simple math. Okay, so circuit 2, I got a bunch of fan coil units, and that's 2 million. So I got a bunch of them I'm stringing up out there in that secondary. So I got 2 million BTUs an hour. And so when I run the math on that, 20-degree delta T, 500, I get 200 GPM. So it's 10 times the first circuit. Well, that makes sense. I'm going to spec these for 150-degree water in and 130 out for a mean water temperature of 140. Then I've got some panel heating equipment, and it's 500,000 BTUs an hour. So that's going to require 50 GPM at a 20-degree delta T. So I'm speccing that at 120 in, 100 out, and 110 mean temperature. And then my air handling, I got some big air handlers. That's going to be 500,000 BTUs an hour. So I need 50 GPM for those. And I'm 190 in and 170 out. Okay. So, and I have selected my primary temperature, supply temperature at 220. Okay. Well, goodness gracious, 220. I've got my flow rate, I got my loads, gosh, this shouldn't be too hard to size everything up. Okay, so let's take a look. And I'm proposing a reverse return system. Okay, so first of all, let's determine the crossover, required crossover flow rates. Okay, well, so I know my supply temperature and I know my return temperature. Okay, so, and these return temperatures just came from right here. That's just what I'm going to have based on what temperature water I want to put into my coils. Okay. So then for each one of these, it's pretty easy. You've got your crossover temperature drop. I'm putting in at 220. I'm coming out at 190. And so I got 200,000 BTUs an hour. So 200,000 divided by 500, the constants divided by 30 is 13.3 GPM. So I've got to take 13.3 GPM out of my crossover loop, or I got to put it into my crossover loop. I got to take it up into my secondary. I haven't shown all the secondary stuff up here. I'm just showing the crossover. Okay. Likewise, for secondary circuit number 2, I've got 2 million BTUs per hour, and my overall crossover drop is 220 in, 130 out. So I got 90. So that's going to require 45 GPM to do that. So, and then the last two, it's the same thing. You just do the math. So for number 3, I've got 8.5 GPM, and number 4, I've got 20 GPM. Well, golly, so let me add those up real quick. So I got 13.3 plus 45 plus 8.5 plus 20. So that's, I got 86.8. And that's total GPM, right? He says 86.6. Well, he ain't right, is he? He can't add. I'm sorry. I disagree with him, but anyway. So I'm going to use my number, store 1. So let's see what the, what do we want to do here? What the return, or what's the delta T, or what's the return temperature to my boiler, okay? So if I add up all of those loads, it's 2 million, 3 million, that's 3.2 million BTUs an hour. So 3200000 divided by the flow rate divided by 500. And it's right about, I get about 74, but he used the wrong number. So he got 75. Anyway, so we get a delta T of about 75. So if we're what, 220 out minus 75, we're going to be about 145 degree water temperature back to the boiler. Okay, so that's pretty simple. So that's how you can size your crossover flow rates. If you got questions, you can jump in there. Let's see, there's some notes. Procedure outlined above differs from conventional practice where distribution flow rates were stated. That's, you just say, okay, so if you size your crossover for 20 degree delta T's on this, he says your distribution flow rate's going to have to be 320 GPM. So say we're down way less than 100 GPM. So that shows the value of, you know, the primary, secondary, and the elevated water temperatures. Does that, oh no, see here he's 86.8. So he's just got a mistake on that figure. You know, mistakes happen. Okay. So I don't know, what are we doing here? 2 pi. Okay, these are examples of control. Okay, and so for our secondary flows, well, let me see, I don't think, yeah, we did size the secondary flows, didn't we? Yeah, we got the secondary flows. Yeah, so we already knew our secondary flows there, 20, 200, 50, and 50. So I guess this is just showing different control options and the crossover flow and all of that. And so then You know, the difference between crossover and secondary is going to mix right in the common pipe. And that's what's going to modulate the temperature that goes out to the secondary. And so he's projecting to do this baseboard control with start stop. Just click the pump on and off. For all of these fan core units, there's a bunch of them because that's a lot of flow for fan core units. We're going to do three-way valve control, and see it's in the crossover with reset that temperature with outside air. And you can see the mix, you know, so 45, so what do we got? 155 GPM bypassing that's mixing right here with this 45 GPM of crossover flow to get us, what was that? I forget the temperature. What was the temperature in that second? That one knocked it way down, didn't it? Yeah, we're mixing to 150 in that secondary. So we'll have 150-degree water here going out through all of these. The panel heating elements, we're going to do a two-way valve. I think this is just showing some different options here. Where we got our balance valve here, opens up. Going to pump this continuously. And then here's my air handler control over here. So that's going to be an injection pump. So we'll put shots of heat up here into this secondary loop when we need it. And then this pump, so the injection pump will start and stop, and the secondary pump will go continuously. Oh, he's also showing you the various flow rates that you would use for pipe sizing, because, you know, when you start out, you're pipe sizing for, you know, 86.8, but once you get up to this point, we're pulling what, 13.3. So in this pipe, I've only got 73.5 GPM. And, you know, that looks like a short pipe, but that could be 100 feet, you know, before you get down to the next one in a real building. And so that pipe would potentially, that's not a lot. It may or may not be downsized, you know, but then we're going to pull out 45 GPM. So now we're down to 28.5. So I guarantee you this pipe size is going to be smaller as we come on down through here. And then from this point, we only got 20 GPM around here, 20 GPM there. And then of course, you know, on your return side, I start out with a small pipe because I only got 13.3 GPM. Then I pick up the 45 and it steps up to 58.3. And I pick up the 8.5. And so it's up to here. And then we get the entire return back around there. Got our air separation compression tank over here, all that stuff going on. Now he's talking here, okay, what if you did this with a direct return? If you did this with a direct return, you would potentially be looking at some significant imbalance depending on the coil pressure drops, you know. So let's see. So he says some things you can do. You can put a flow meter indicator in the crossover. That's supposed to help. He recommends both of these. And the other thing you can do is you can select that control valve in the crossover for a high pressure drop compared to all of the circuits. So say one circuit might be 10 feet, the other circuit might be 50 feet, but if I put a 50-foot control valve in there, or you say I reduce the percent difference between it, which makes it easier to balance. Now you'd have to run the numbers before you decided whether that was a good idea, because that's extra head that your primary pump is going to see, because that's in the crossover. So that may or may not be a good idea. This is where this thing really kind of jumps off the deep end a little bit. I mean, from here, pretty much the rest of this thing is this one pipe primary main design. And so I'll just show you a little bit of this. I'm not going to go through all this because I don't think very many people are going to design this. I mean, they can make it work for an example here that has 4 secondaries, but if you have a big building with lots of secondaries, I just don't think this is going to work for you, because what happens is we're starting off with 240-degree water. So then he pulls, you know, whatever he wants, whatever the capacity of this coil is, 200,000 BTUs an hour, and this temperature drops because he just pulls water out of this and dumps it right back into the primary supply. There's only one pipe. It's a one-pipe primary. And so every time you go across a secondary, you lower your water temperature. Well, those poor guys out there on the end of the system, come on, man, it's cold in here. Give me some water. You know, I started out at 240, but that's on the other side of the building. You know, of course, all that's got to be taken into consideration. And he does that very carefully as he goes through all of it. But I'm just not sure that this is a very practical. If I was designing a system, I would not look at a one pipe primary unless I was somehow forced into it, you see. And so then he comes along and he calculates, well, what's my primary water temperature as I go around the loop? Well, so I wind up over here, and of course the design parameter, this last zone needs 190. So he has to have enough temperature and flow, enough heat over here that he can still have 190-degree water here, because that's exactly what he has to pull up into this circuit, because that's the spec on the circuit. And so that's his, say this number, say supply temperature, number 4 is 190. And so he runs a calculation for the first 3 to make sure that he still has 190-degree water here. And then it goes on from there. But it's long and fairly detailed. It's there if you want to look at it. I'm not going to test you over it. I do not consider it to be terribly practical, even though from an educational standpoint, I mean, it would be good to work through all that just to make sure that you understand the concepts. So with that, I think I'm going to stop today's presentation. Oh, we've gone pretty much an hour, so that's pretty good. So final, now Nick, keep me straight. Final on Monday at 10:30 to 12:30, and it'll be over VRF. Thank you, Nick. I left that off the list. Air control, control valve sizing, and primary, secondary up to this point. I will not include one pipe primary. It could be some short, because, you know, I probably will ask you to calculate some CVs. So that, you know, Q is equal to 500 GPM delta T. I don't consider that to be, you know, over the top. And I don't know if we did any other little calculations along the way. They don't really come to mind right now. But when you go through those presentations, if there are any simple little calculations, just brush up on them and be ready. So it'll be in iLearn. I'll have it ready to open up at 10:30. You'll have 2 hours to do it, and good luck. And I'll get all this stuff posted. And I've enjoyed it. You guys have been great to work with. If ever I can help you with a reference or anything, you just have a technical question, you get out there working, you want to bounce it off of me, feel free to email me. As long as tech lets me keep my tech email, I guess I'll set up a Gmail account here before long. But I think I have one, but I don't ever use it, and I don't even remember the login to it, to be honest with you. But so I think that's a wrap. Again, let me know if I can help you, and the exam is Monday, 10:30. So good luck.